done with the Avogadro's law, and there's a little bit more to that, and we'll get to it when we get into some gas stoichiometry. But the next one is going to be our ideal gas law. And the ideal gas law is simply a way to relate all of our gas laws together. That means we're going to relate Boyle's law, Charles' law, Gay-Lussac's, Avogadro's, and the combined gas law all into one. And here is the formula. The formula is PV equals nRT. Let's go over these variables real quick. P stands for pressure. And you remember that pressure can be in atmospheres, millimeters of mercury, kilopascals, inches of mercury, pounds per square inch. We have lots of different ways that we can describe pressure in a lot of different units. Go on to the V, and the V stands for volume. And when we're doing these ideal gas laws, we want the volume always to be in liters. And you'll see why here in a second. The N stands for moles. I don't know why it's not an M, but it's not. It's an N, and it stands for moles. And you know how to go from moles to grams or grams to moles. So you'll be going to be doing lots of that. The R is what is called the ideal gas constant. And on my next slide, I will show you the ideal gas constant. It is different for each pressure. So therefore, you have to know what your pressure is in before you know what the R value is. And then finally, the T, that stands for temperature like always. And remember, when we're doing any gas law problem, the temperature must be in Kelvin. Let's go to the next slide. Here's a picture out of the book, and you can see right here the numerical value for R. And it changes from 62.4 to 0.0821 to 8.314. And it depends on the units of pressure. And it depends on the volume, but we're going to make sure that the volume is always in liters. We're not going to worry about this cubic meters. We're going to have it in liters. And you'll see that if it is in millimeters of mercury, if the pressure is, then the R value, that constant, is 62.4. In the same problem, if the pressure, if we converted the pressure to kilopascals, we would also have to change our R value. Let's look at a problem and we'll see if we can figure this out. So here's the first sample problem. It says, what is the pressure in atmospheres exerted by a 0.5 mole sample of nitrogen gas in a 10.0 liter container at 298. So the first thing that we're going to do is we're going to write down our formula. We're going to write down PV equals nRT, and let's fill in what we know. So we have PV equals nRT. My camera went to sleep. How about that? Well, we know that the volume is 10.0 liters. We want to know the pressure. The moles. We have, it is 0.5 moles. Am I correct on that? That is not 0.5 moles. Yes, I was correct. So we have 0.5 moles. Now, what is our pressure? Well, the question said, what is the pressure in atmospheres? Well, what is the R value for atmospheres? Here's the pressure value in atmospheres, ATM. So the R value is 0.0821. 0.0821. So as you can see, I've plugged in my R value. And then finally the T value. the T value, the temperature was 298 Kelvin. Well, to solve this, I'm simply going to, get rid of the 10. So we're going to divide by 10, and we're going to divide this whole side by 10. So let's do that. So the pressure equals, so let's take 0.5 times 0.0821 times 298 divided by 10. And I get 1.22 ATM. Let's do a second problem real quick. Here's the second problem. The second problem says, if a 3 mole sample of oxygen gas has a volume of 1.5 liters and is held at 1.02.5 kilopascals, what will be the temperature of the sample? And we know the temperature of the sample is going to be in Kelvin. So let's go ahead and do this second problem. So let's start. Let's go PV equals nRT. And we know the pressure, it was 102.5, and those are kilopascals. The volume was 1.5 liters. The moles, we had 3 moles. The R value, well, let's go back and look. R value. R value for kilopascals. R value for kilopascals is 8.314. And we're looking for temperature. Let me get this over here a little bit. And we're looking for temperature. Well, if I multiply these two, I get 153.75, and then 3 times 8 is 24.942. Let's divide by our 24.942. Let's divide by 24.942, and I get a temperature of 6.16 Kelvin. See if that's what you get.